Okay, year 12. Now, today we're just going to review skewness to start off with because we need that concept for the next exercise. Now, if you remember back from year 10, maybe even year 9, you had positively and negatively skewed distributions. So positively skewed means the mean is to the right of the mode because of the large scores to the right. Another way of thinking of it is the tail goes off towards the right. Okay, so here are two examples of positively skewed distributions. You can see the peak is to the left and the tail is to the right. I always think of the tail as pointing towards the positive end of the number line. Okay, negatively skewed distribution. The mean is to the left of the mode because of the very small scores to the left. So you can see here that negatively skewed, the tail goes off to the left. The bump is to the right. Here are two examples of negatively skewed distributions. I like to think of negatively skewed as the tail pointing to the negative end of the number line. Okay, so we need those two ideas for the mean and variance of a binomial distribution. Okay, so let's start off with the first example. We've got to graph each binomial distribution and describe its shape. So let's look at part A. Probability of success, P equals 0.2, and the number of Bernoulli trials, N equals 8. So remember we looked at this for the binomial distribution formula. We can define it as in terms of P and Q, where P is the probability of success and Q is the probability of failure, or we can define the formula purely in terms of the P variable. Okay, so for part A, we're told P is 0.2. We're told that there's 8 Bernoulli trials. So starting off with X equals 0, subbing that into the formula, we get 0.168. Now, we need to keep going with that. So X equals 0, the next one is X equals 1, then X equals 2, all the way up to X equals 8. Okay, so if we calculate the probability for each outcome, starting from X equals 0 all the way up to X equals 8, here are our values. Now we can plot all of those as a column graph. So if you look at for X equals 0, we go up to 0.168, there it is. For the probability of X equal to 1, we get 0.336, so it goes all the way up here, and so on. So we can plot each of these numbers here as a column graph. Okay, so probability is on the vertical axis and the random variable on the horizontal axis. You can see here the graph is positively skewed. Okay, so if we were to draw that as a smooth curve, doing my best with the graphics tablet, here we go, and then down. You can see here that the tail goes off towards the right, towards the positive end, if you like. So it's positively skewed. Now, for part B, we can do the same thing. This time they give you the probability of success is 0.5, number of Bernoulli trials is 8. So we do the same thing for part B, calculate all the individual probabilities, starting with P of 0, P of 1, all the way down to P of 8, and drawing the same type of graph again. You can see that the symmetry in this column graph going up and then down. Whoops, there we go. All right. So symmetrical kind of shape there. So not positively or negatively skewed, they're just symmetrical. Now for part C, if you go back to part C, this time the probability of success is 0.7 and the number of Bernoulli trials is 8. So doing exactly the same thing again. Here we go, we calculate all the individual probabilities and then we draw a column graph to show that. So you can see here that we are getting a negatively skewed distribution. Okay. All right, so what can we say about those three examples? Well, if the probability of success is less than 0.5, the distribution is positively skewed. If it's equal to 0.5, such as tossing heads or tails, is an example where you get 0.5 as a probability of success, then the distribution is symmetrical. We say it's a normal distribution. And then if the probability of success is greater than a half, the distribution is negatively skewed. Okay. Now, let's have a look. In a previous exercise, we're going to look at the mean of the binomial distribution. In the previous exercise, we established that the mean of the Bernoulli distribution is P. So if you've got, for a binomial distribution, n Bernoulli trials, then the mean, or the expected value of the binomial distribution, is NP. Okay, so just n lots of p there. So if you look at a proof here, so x is our random variable, and bin meaning binomial. So if x is a binomial distribution with n Bernoulli trials and p the probability of success, then we write this down. X consists of the n Bernoulli trials, x1, x2, all the way up to xn. Then the expected value of your random variable x will be the expected value of x1 plus, that should be x2 there. My bad there. x2 all the way up to xn. And now, as the trials are independent, the expected value of the sum of those Bernoulli trials is the sum of the individual expected values, okay? Because the trials are independent. So that means E of x is E of x1 plus E of x2 all the way up to E of xn. Now we know that the mean of a Bernoulli distribution is P. So P there, all the way up to P. That gives you how many P's? It gives you n lots of P's because you could have n trials. Okay, so the expected value of a binomial distribution is n times P, where P is the probability of success and n is the number of Bernoulli trials. Now, also, what else did we do? We established, we looked at variance before. Now, the variance of a binomial distribution is n p brackets 1 minus p. So let's have a look at a proof of that. Okay, so proof. Alrighty. So again, this notation means if x is a binomial distribution with n Bernoulli trials and p the probability of success. Okay, we've got the n Bernoulli trials x1, x2, all the way up to xn. Okay, so the variance of x, our random variable, is the variance of x1, that should be x2, again, sorry, all the way up to xn. Now, as the trials are independent, the variance of the sum of those Bernoulli trials will be the sum of the variance of the individual Bernoulli trials. Okay, so variance of x1 plus variance of x2 all the way up to variance of xn. Okay, now the variance of x we established before was p1 minus p in the previous exercise. So each one of these will be p1 minus p, and we have n lots of those. So we end up with the variance being n times p1 minus p for a binomial distribution. Okay, so the variance of a binomial distribution is n lots of p1 minus p. Okay, so let's have a look at some examples. Let's put some numbers to these formulas. Okay, so find the mean and variance of each binomial distribution. Okay, so let's start off with part A. Okay, so for part A, we have the probability. Now, tails is our probability of success that we're looking at. So probability of tails is equal to a half. All right, so that means for our binomial distribution, we're going to look at p is equal to a half. Now, n is the number of Bernoulli trials. It's going to be 100. All righty. So the mean, or the expected value, is according to our formula that we just proved. And that should be, my bad there, x. Okay, E of x equals n Bernoulli trials times the probability of success. Okay, so 100 times a half, which equals 50. Done. All right, so certainly out of 100 times, tossing the coin, you'd expect tails to occur 50 times. All right, now part B. Actually, no, not to part B, because it did say calculate mean and variance. All right, I'll do variance over here. So let's look at the variance. Okay, so variance. Let's just write down the formula that we just proved. So n outside of p. Don't need that one. Yeah. 1 minus p. Okay, so n Bernoulli trials. Probability of success is a half. 1 minus p is also a half. Okay, so you should end up with 100 times a quarter, which is 25. Done. All right, let's look at the next one. Okay, so a pair of dice is rolled 120 times, and the sum of 8 is 8 recorded as a success. Okay, so the sum of 8. Now, all together, now we could do a little table here, but what are the possibilities for getting 8? We could have 1 and 7, 7 and 1, 2 and 6, 6 and 2, 3 and 5, 5 and 3, and we could also have 4 and 4. Now, when I roll a dice, or 2 dice that is, I have 36 possibilities, don't I? Okay, so out of 36, all right, what's the probability of success? 1, 2, 3, 4, 5, 6, 7, where I've got a sum of 8. Whoops, my bad there. What am I doing? These aren't right, are they? I can't get 1 and 7. Okay, so I'll rub those out. That's not quite correct, is it? Now that's correct, because I don't get, there we go. 1, 2, 3, 4, 5. All right, so 5 out of 36. That's good. Now, that means my probability of success is 5 over 36. Okay, so if I'm looking at my mean, right, or as we say, our expected value, okay, that's just n lots of p, isn't it? Right, now your Bernoulli trials, the number of Bernoulli trials is 120, and 5 over 36, and that gives you 16 and 2/3. All right, good. All right, let's see if we can squeeze in the variance down here. All right, so the variance r of x is n lots of P, 1 minus P. So that is 120 times the probability of success, 536 times by 1 minus P. So that's 31 on 36. Okay. And that gives me a final answer of 14 and 19 on 54. Okay. And that's it.